If a nuclear bomb destroyed Hiroshima in 1945, how is it possible that the city still exists today, while Chernobyl, which never suffered an attack, remains abandoned decades later? At first glance, the question seems simple, but it hides a common misunderstanding about how nuclear energy works. Many people assume that any nuclear event is the same, but physics shows that these two cases are completely different. In Hiroshima, the explosion was instant and concentrated, while in Chernobyl, the disaster involved the prolonged release of radiation interacting with the ground and environment over several days. Understanding these differences is crucial to separating facts from myths. It all starts with the discovery of nuclear fission in the late 1930s. Scientists realized that the uranium nucleus could split apart, releasing enormous amounts of energy suddenly. For a single atom, the effect is almost negligible. But when trillions of atoms split, the energy released is immense. From this discovery, two distinct paths emerged. Release this energy in a controlled way, generating electricity in reactors, or release it all at once, producing a devastating explosion. The underlying physics is the same, but how the energy is released and its practical consequences are radically different. In the case of the Hiroshima bomb, the goal was to release maximum energy in fractions of a second. The detonation occurred in the air using a relatively small amount of highly enriched uranium. The initial radiation wave was intense, but very brief, and radioactive material dispersed quickly into the atmosphere. The human impact was catastrophic, but the environment did not become permanently uninhabitable. In contrast, the Chernobyl disaster involved a reactor containing hundreds of tons of nuclear fuel. When the accident occurred, the energy was not released instantly, but over several days, interacting with the soil, water, and surrounding environment. The difference is not in the instant power of the event, but in how radiation was released and how it interacted with the environment. A central point is the difference between nuclear fission and a nuclear explosion. Fission is the physical process of splitting the nucleus, but an explosion depends on the concentration of material and the speed of the reaction. Nuclear bombs require highly enriched uranium, over 90% uranium-235, to ensure that each neutron triggers an uncontrolled chain reaction. Reactors, on the other hand, operate with low enriched uranium, usually between 3 and 5%, allowing the reaction to be controlled. Control systems and absorbent materials prevent the reaction from escaping safe limits. This fundamental difference explains why reactors cannot explode like bombs. The Chernobyl reactor, an RBMK type, had serious structural flaws. Designed in the 1950s, its original goal was to produce plutonium for weapons, with electricity as a byproduct. Unlike modern reactors, it used graphite as a moderator, had no robust containment, and exhibited unstable behavior. As temperature increased, power also increased, creating a dangerous feedback loop. During a poorly planned test, safety systems were turned off, control rods were withdrawn beyond safe limits, and reactor warnings were ignored. When operators tried to shut it down, the control mechanism initially made the situation worse, leading to a core rupture, steam explosion, and graphite fire, releasing massive amounts of radioactive material. It was not a nuclear explosion, but a structural collapse with prolonged catastrophic effects. Another crucial detail is time. Radiation is not just about intensity. Duration matters. Hiroshima released energy in microseconds, with intense but brief radiation, no continuous source. Chernobyl released radioactive material over several days, with particles spreading into the soil, water, and air, contaminating plants, animals, and the food chain. This explains why Hiroshima could be rebuilt, while Chernobyl became an exclusion zone. The mistake is assuming all nuclear events are the same, and that instant intensity is equal to prolonged exposure. Beyond physics, there is the social and psychological impact. Chernobyl became a symbol of invisible danger, creating strong narratives that persist even against statistical evidence. Generalizing one extreme case as a rule for all nuclear technology is misleading. Statistically, nuclear energy causes fewer deaths than coal, oil, natural gas, and even hydroelectric plants in major accidents. Yet fear does not respond to numbers, and rejecting nuclear energy has led many countries to rely more on fossil fuels, worsening emissions, climate impacts, and public health. A rare risk generated acceptance of far greater risks. In summary, Hiroshima exists, Chernobyl happened, and both are explained by physics. Hiroshima had little material, an airburst, and brief radiation. Chernobyl had massive fuel, prolonged release, and persistent contamination. Understanding this does not erase human tragedies, but prevents them from being used as misleading arguments. Science does not shout, but it explains. When we replace fear and intuition with knowledge, misinformation loses power, and facts become stronger than misleading narratives. If you found this content useful, make sure to subscribe, hit the like button, and leave a comment below to help share accurate science and knowledge with everyone.